formal power series. So today what I'd like to talk about is some ideas, I think some pretty simple ideas that let you get validated computer-assisted error bounds, mathematically rigorous bounds, for those formal series expansions that you computed on your computer. So remember we talked about Taylor integrators. For initial conditions, for a flow box, for submanifolds, all kinds of Taylor integrators. And also Taylor expansions of, for the parameterization method. And those were the ingredients for computing connecting orbits. Okay, and in both cases, I was thinking about analytic vector fields. Okay, so the approach I'm going to discuss today is inspired by this paper, Existence and Stability of Traveling Pulse Solutions of the Fitz-Unagumo Equation by Hans Koch and Gianni Arioli in 2014. And this paper was, well, first of all, they proved the existence of some traveling pulse solutions for the PDE, Fitz-Unagumo. They did this by studying connecting orbits, a lot like what I was talking about yesterday, right? So they reduced to the problem of looking for traveling pulse solutions for a PDE. They reduced this to the problem of finding homoclinic or heteroclinic solutions for an ordinary differential equation, and then they used the computer to prove the existence of those homoclinic or heteroclinic solutions. Okay, so it's like the kinds of things I wanted to do yesterday. They also compute in a mathematically rigorous way the Evans function for those traveling waves so that they can compute stability for the equilibrium of the PDE. Okay, but so there's a lot of nice stuff in this paper, but somewhere buried inside the paper they also introduce what was the new idea for doing validated computations for Taylor series methods, and that idea is what I'm going to talk about today. Okay, but first, let me say just a couple of things, couple of more things about the Frechet calculus. There are a couple of things that, especially since this is a school, I was thinking this morning that John Philippe and I have been using rather glibly, I guess. And let me just, I'll say these two things explicitly and prove one of them. Okay? So the first thing is, if you have a Frechet differentiable map, so let's say if f from x to y so this is Frechet differentiable at x0 in x, and now you have a bounded linear operator, let's say on y. Okay, it could even go into another space, but an A is a okay. Then you can differentiate A times F, and it's A times dF, right? So this is like the generalization of the fact that, d dx, a f of x in freshman calculus is a d dxf, right? This is the generalization of this to infinite dimensions, right? So probably, everybody knows this, but if you haven't sat down and proved this at some point, it's a nice exercise. The other thing I'll say is, suppose that X and star is a Banach algebra, a commutative Banach algebra. Okay, so the Banach algebras we've been working with have been commutative, right? The discrete convolution for Fourier series is commutative. The Cauchy products are commutative. So suppose you have a commutative Banach algebra, okay? And let's say you define the map. Let's say f of A is A star A. Okay? So this is a smooth map. So dfa acting on H is 2A convolved with H. Okay? So again, it's very much like the formula from freshman calculus. And then you can generalize this to multiple products, you know, A times itself n times. You get the formula you expect. And, you know, I guess I was thinking I'll show the proof of this, okay? Just because it's a school and I should prove a couple of things, right? So for this, what do? You know, of course, you look at f of A plus H minus f of A. What is that? That's A plus H convolved with A plus H minus A convolved with A. This is A convolved with A plus H convolved with A plus A convolved with H plus H convolved with H. So these cancel, and since it's a commutative Banach algebra, you have 2 A star H, okay, which that wouldn't happen if you didn't have commutativity. So what do? You know, I want to show that this is my derivative, right? So I need to look at the limit as H goes to 0, f of A plus H minus f of A minus the thing I think is the derivative, 2A star H. Right? And so this will be the limit as H approaches 0, okay, of, so this was f of A plus H minus A, so this is 2A H plus H star H minus 2A H. So this is just H star H over H. And this is 0 as H star H is less than or equal to H using the Banach algebra now. And that goes to 0 as H goes to 0, right? Okay, so this is what's, you know, John Philippe was doing a lot of calculus with these Banach algebras yesterday, and this is the kind of thing that's making all that work. Okay? So now let me go back to nonlinear recurrence relations. And basically what I want to do, I'm going to try to illustrate this method by working an easy problem. Okay? And then I'm going to wave my hands about how things generalize. But so yesterday we had examples like x prime equals negative x plus x squared, say an initial value problem. Okay, and we wanted to find a solution. Actually, first let me rescale time, okay, because that'll be, it never hurts, it doesn't change the solution curve, and it'll actually give me some control over Taylor series coefficients. So the equation I really want to look at today is this one. Okay, with the same initial conditions. So then we look for x of t is some, you know, as a power series. We look for a power series solution, and this led to these recurrence relations. A n is x0. If n equals 0, n is L over n negative a plus a convolve with a. Okay, the n minus 1th component of that if n greater than or equal to 1. Okay, so this was recursion that let us compute as many Taylor coefficients as we wanted. But at some point you stop, right? And you have just on your computer a finite polynomial approximation. So if you use interval arithmetic, using interval arithmetic, you can get what I'll call a bar you can get this infinite sequence, right? Okay, so that these are exactly the Taylor coefficients of your solution, right? You can enclose them in intervals, so you know these exist and they're unique and they solve this recursion exactly, okay? So what you want something like a sequence like this. Okay, a sequence that's just a tail, so that a bar plus a tail is the solution of the recurrence to all orders, okay? Okay. Now you're not going to be able to explicitly compute these like you did with the first n, but maybe you can bound them in some Banach space. So that's what I'd like to do, right? So I'm going to set up a fixed point problem that is solved by this tail sequence. Okay, so define, here's the Banach space I want to work in. It's the set of all sequences in L nu 1. Okay, so remember, you're in L nu 1 if you're an infinite sequence and you have norm. This is your norm on L nu 1, right? It's the sum n equals 0 to infinity, the modulus of the coefficients. Let me call that un times the weight. Nu n. Okay, so first of all, I want to be in this space, but second of all, I want un to be 0 if n is between 0 and n. So this is like the set of all allowable perturbations of my approximate solution a bar. These guys are fine. I don't want to do anything to them, right? I just want to perturb the tail so that I get a true solution, right? Okay. So this x, it's an exercise to check. X is closed in L nu 1. So since it's a closed subset of a Banach space, well, okay, you can also check that X is a vector space. So it's a closed linear subspace. It's not just a closed set, but it's a closed linear. So it's a Banach space. Yeah.
One question. You said that when you have computed the coefficients A0 to n, you say that in the next iteration, these coefficients are not going to change.
what I'm saying is I've computed up to order n, and I consider these exact now because I have interval enclosures of the exact guys, using interval arithmetic to evaluate this recursion. Okay, so these are basically the exact Taylor coefficients to order n. So what I'm saying is this is a space of perturbations to that approximate solution, and these are the perturbations I want because they don't destroy what's already good. This is all I'm saying. Does it make sense?
Because, well, when you use the Picard method to compute the Taylor series of the solution of OD, if you start
I understand.
with the first coefficient.
This is a lot like doing the Picard method, but it's in the sequence space. So it's closer to what I'm doing on my computer. But I mean, there's, you know, of course it's the, what else could it be, right? It's somehow the Picard method. Yeah. Okay? Okay. So this is a, but you know, I want to do explicit, I want explicit bounds, right? Yeah. Okay, this is a closed subset. It's also a subalgebra, right? So if U and V are in X, then U star V is in X, okay? In addition to that, if C is any sequence in L nu 1, and U is in X, so it's a tail, then C convolve with U is a tail. Okay, so these are nice facts that'll be useful later. So now I want to define a map. T from X to X by okay. T of U, I need to tell you the nth coefficient, this, you know, U is an infinite sequence. T of U is going to be a new infinite sequence. I need to tell you the entries of that infinite sequence. So T is 0 if n is between 0 and n. So for sure we're staying in X. And T is my recurrence relation, Ln. Okay, let me be a tiny bit careful. Let me show you what I'm going to write. I'm going to write this recurrence relation, but I want to find A as A bar plus U. You know, that's what I want my solution to look like. So this fixed point operator is minus A bar minus U plus A bar plus U convolve with A bar plus U. And it's the n minus 1th component of that sequence if n is greater than or equal to n plus 1. So you can check that this is a map from X to, well, certainly sequences that are 0. You can also check that this maps if U has bounded L1 norm, then T of U will have bounded L1 norm. Okay, that uses the Banach algebra and the fact that these constants are actually decreasing. Okay? Okay, so if U, let's say tilde in X, has T U tilde equals U tilde, then A bar plus U tilde solve the recurrence relation exactly. Okay, so this is not hard to convince yourself. I mean, this is just the rest of that recursion relation for all the bigger n's. Okay, so now I want to goof around with this t for a minute and write it in a better way, or more convenient way, let's say. Okay, so I want to decompose t into two easy to understand pieces. Okay, so let me define a linear operator, L from x to x by L of h, the nth component of that, okay, is 0 if you're in the first n components. So if h started in x, it's staying in x, and it's L over n, hn minus 1, if n greater than or equal to n plus 1. So this is like a shift and division by n. Okay, so this should be a nice kind of smoothing operator. It's easy to see that this is linear. Okay. L is a bounded. That's probably not surprising at all, but there's a nice estimate. L as a bounded linear operator on x, that norm is less than or equal to L nu over n plus 1. A nice bound on this operator. I'll do that again because it's a school, so we should have a little fun, right? Or something. So maybe you've already done it in your head. So we'll look at L, H. Okay, so I need to take H in X first. Okay, and I'm going to look at the norm of H. This is the sum n equals n plus 1 to infinity of L, H, n, nu n. Right? So that's n equals n plus 1 to infinity. We'll just write down the formula. L over n, h n minus 1. Yes? Okay. Okay, so this is, and let's say we rescale time in a positive way, otherwise I'll put an absolute value there. I'll take the L out, I'm going to re-index to start at n. So little n is big N to infinity. This will be 1 over n plus 1. This will be hn, nu to the n plus 1. I'll take a nu out. Okay, this is less than or equal to L nu over whatever the smallest this coefficient ever is, the biggest it ever is. The biggest it ever is n plus 1. And then we have the norm of h. Okay, so if I take the sup over all h with norm 1, with, yeah? Then you get this bound, of course, right? Okay, so this operator is nice because it's kind of the complicated part of what's happening here. Okay, so now I can write t in kind of a more high-level form, right? Without all the indices, I can say t of u. It's this linear operator L acting on minus a bar minus u plus a bar. Okay, and that's it. Right? Okay, so I want a fixed point of this thing. What I'd like to do is show it's a contraction. And what you might be starting to believe is that if n plus 1 is big enough, there's really hope that this is a contraction. Now I also have nu, which you think of as your time step here. So if you were doing the Picard, you would control things with your time step. But I want to take big time steps. So I want to control things with the order, if possible. Okay. Okay, so I want to find a fixed point. So I'll try to do the contraction mapping theorem. So let's see. The first thing I should do is compute the derivative, right? And because of the little bit of calculus that was on the board at the beginning, you know, we have that tu is, let's see, it's L of negative a bar. Okay, let me kind of okay, this is t. So I have constant stuff. Then I have, so that's this and this. I have linear stuff. And I have nonlinear stuff. So I'll take the derivative. So dtu acting on some h. This is gone because it's constant. This is linear. You know what? I should have had the bullet point earlier when I was sort of collecting things about Frechet calculus. But so just note, right? The Frechet derivative of a linear map is the linear map. Right? So this linear part that's my derivative, okay? And the nonlinear part, the derivative goes past this linear operator that acts like a constant, and the derivative just like the quadratic function in the Banach algebra. So this is 2L U star H. Right? Okay, so let's see. dtu acting on h and x. This is less than or equal to the norm of L. Actually, now that I've done that calculus, let me put things back together kind of. Right? That's my derivative. So the L appears there once. Then I need the norm of negative h plus 2a involved with h plus 2u So with the triangle inequality and that estimate, this is norm of h plus 2 norm of a bar, your numerical approximation. So norm of h plus 2u h. Okay, so this is as if we're on the whole space. So if I take the sup over h with norm 1, I have that my operator norm for t okay, I have this. But if I consider that in a ball about 0, So in this case, what's my approximate solution to the fixed point problem I'm trying to solve? Not to the original problem where we did all the recursion, but my approximate solution to the tail is 0, right? So I'm going to do a contraction argument just around 0, which is my approximate tail, okay? So if you take the sup over all u and the ball of radius r about 0 in x of the derivative, this is now just L nu n plus 1, 1, 2 times the L nu norm of your numerical approximation plus 2 times the size of whatever ball you picked. Okay? Okay, so now you maybe really can start to believe that I have some options for making that derivative less than 1, right? Okay. Any questions so far? I feel like I've been writing kind of for a long time. No? I mean, it's almost like freshman calculus, right? Okay, so let's see. This is important, so maybe I'll copy that somewhere. So I guess a few things are important that I've done. So t, u, let's see, t from x to x, that's L negative a bar minus u, a bar plus u convolve with a bar plus u. Okay, that's my operator. And now I have that the sup u in a ball of radius dtu is less than or equal to. Okay, there's one more. One more estimate I'd like to do, and then we can validate this Taylor. We can do a validated integration. Wait, I mean, so let me also show you that where does t send my approximate solution? Okay, this is in x, so that's the sum n equals n plus 1 to infinity, t0 n, right? But t0, that means u is 0. This is L of negative a bar plus a bar convolve with a bar. That's it, right? And if now I'm writing things in components, I'll write this as L over n plus 1. No, L over n. So that's the number L over n. And then I have to shift, right? So I'm kind of going back to the formulas we had at the beginning. Okay, I need to like look one time at this formula. Okay, so let's take the L out, reindex again. Take out nu, so L nu. Yeah. And then the thing is that this is a finite sum, right? Because A has only finitely many terms, a bar. Remember that a bar is a0 through an. My finite Taylor series sitting on my computer. Okay? So, you know, if I convolve a bar star, a bar Cauchy product A, it has non-zero terms for n between 0 and 2n, because if you take polynomials of order n and multiply them together, you get a polynomial of order 2n. So and I'm not going to do any triangle inequality or anything else with this. I'm not going to take this 1 over n out, because this is a finite sum that I would compute on my computer. I don't want to spit on my luck here. Applying triangle inequalities and estimating, you know, I'm just adding up a bunch of numbers. Why would I just add them up, right? So this I'm going to name y0. Okay? So I have, actually there's no inequalities there, right? This is just, that is this, right? Okay. So now I have a lemma. I basically have just proven the following. Okay? So for nu greater than 0, define y0 just like that, right? y0 to be L nu sum n equals n to 2n. And z r to be this, right? To be L nu over n plus 1, 1 plus 2, a bar plus 2r. Okay, these are things that you can do in a computer. You pick an r, you pick a nu, you tell me you're rescaling, you compute to some order n, this is all fixed. This is your approximate solution now, your Taylor coefficients to order n. Everything's sitting on a computer, so these are numbers that you compute, right? Okay. Do they get you anything? So define these. And P R to be just Z R times R minus R plus Y0. Okay? And this is actually a quadratic polynomial in R. Right? So define PR like this. If there is an r greater than 0, so that p r less than 0, then there is a unique Of course, this is an initial value problem, so if it's there, you know it's unique already. But you know, you could be doing something other than an initial value problem here. The parameterization validations go exactly like this. Okay, but so there's a unique u tilde in the ball of radius r about 0, so that t u tilde is u tilde. Okay, let me, just because this is the littlest bit different from the theorem we've been using, okay, let me do this It's very short. It's easier than the one on the first day. What time is it?
4:46.
4:46? Yeah, I'll do it, because then I'll more or less be done. Okay, modulo some comments. Okay, so suppose that what? R greater than 0 and P R less than 0. Okay, what are you going to do? Let's choose U and the ball of radius R about 0. What would I like to see? I'd like to see that T maps that ball into itself. Okay? So what do I care about? I care about T of U minus the center of the ball, but that's just T of U. Right? Okay. I'll add and subtract T0. Yes? So this is an inequality. Okay? This is less than Y0. This is less than the sup, W in BR0, the derivative, right? U minus 0, right? Okay, but that, this is that Z of R, and that bounds this derivative. So this is Z R. And then U is less than or equal to R, right? So, okay, if you look at this thing, right, I have that Z R times R plus Y0 is less than R if the whole thing is negative, right? So this is less than R, and T of U is in the ball. It's actually in the open ball, which is a subset of the closed ball. Because if you picked a guy in the boundary, you would have moved inside. Okay, so this thing maps that ball into itself. Now I just need to, this is the bound on the derivative, right? So, being a contraction is the same, or it's enough to have derivative less than 1. So let's go back to this thing and divide by R. But Y0 and R are both positive. So, this is just kind of collecting the sufficient conditions we need to satisfy the contraction mapping theorem. That's this polynomial encodes that. So T is a contraction on a complete metric space BR subset of X. Right? So there's a unique fixed point, right? Which we know is globally unique because we're doing an initial value problem. So that's the only one in X, in all of X. But I guess that's it, right? Okay, so this leads to just about the easiest computer-assisted proofs I've ever done, certainly outside of finite dimensional proofs, which are sometimes easy, but actually sometimes harder than this. So what do? We compute our Taylor coefficients to some order. We compute this number, we compute that number, and we solve a quadratic equation. Okay, if that quadratic equation has positive real roots, then we have bounds on our error bounds for our Taylor integrator, right? Computer-assisted error bounds. So, are there questions? Yes, sir. My time step will be new, and I'll have to pick new.
But when you were describing integration,
sure, then I have to glue these together. Proof upon proof upon proof upon proof, right? So I take the output of my last step, that's the new input. So, you know, imagine you're just doing, you're flowing x0. So you flow it, and you get phi of x0 for some time, but you don't really know this number. You have it enclosed in an interval. So that interval goes into your next Taylor computation. And this is a kind of wrapping effect, right? So those errors feed forward. So you'd like them to be at each step as small as possible.
Yeah, because it keeps getting worse, right? Every step.
As we all know, right? Okay. Let's see, maybe I can make just a remark about the parameterization method. Or maybe I should, I think I'll just stop, and if people have questions, then we can talk.
do something like more tailored. We control somehow the error of steps further away by taking more the first steps into more.
You know, like there's all kinds of heuristic strategies you could use for this, and then it becomes very much like, you know, adaptive meshing and numerical. I mean, you just use every trick you know, right? It's just that, well, yeah. But, you know, that's one reason when we grow these manifolds, we like to start with a big parameterized manifold. We start with a big parameterized manifold with, say, machine precision error. You know, that's better than starting at the linear approximation and having to recover all of that by doing Taylor integration, right? Or in many problems. Yeah.
So extended precision might be of use, right?
Extended precision, if you don't mind waiting, it lets you push this as far as you want somehow, right? Yeah, it depends on how important it is and how long is a long wait, right? Overnight is perfect.
Yes.
If I come back with my coffee and the computer just finished, I'm delighted, but you know, come on.
But I mean, the growth with the precision is not too bad, right? Like,
I mean, you know, these pictures I was showing you that Shane was doing, you start with machine precision, you go and go and go until you hit 10 to the minus 4, you know? And if you wanted to, you could go a little further, but at some point you have to say, so if you wanted to do better than what the pictures I was showing you, you know, you have to start really getting in there and making improvements and probably thinking harder about how to remesh things, you know. This is, I think for the one step, we have a very nice understanding of what's happening on this. But when you start gluing things together, it's certainly complicated.
well, of course, the problem is that the manifold is not compact.
Yes, the manifold
It's like
is fighting you.
really large.
Yeah. And sometimes extremely curved, right? Yeah. High derivatives. Yeah. Yeah.
Somehow parameterize the error. I mean, you think of the error as some kind of ball around each point, but you also parameterize perhaps that. Does it make sense?
Oh, okay, so I mean, sometimes you do so if we did this same problem with a Newton-like approach, which we've also done, and this works great, and you actually, sometimes you get a little better error bounds, then you don't have to represent your approximate solution in intervals, as intervals. You represent them as just floating point numbers plus a ball, exactly like you say. And then you're just pushing those things around. So this is a little more complicated than that in that I have to have interval enclosures of all of these coefficients. Whereas if I did the Newton-like thing, remember from the first day, my approximate solution only had to be floating point. right? Here I need these coefficients like exactly to nth order. So that's a difference between this. Yeah. Okay, and there are like fantastic improvements on this that can be made if you use, like John Philippe has papers using Chebyshev series to do this. But you know, I wanted to show something that I think is very easy. You know, and okay, a nice thing about this, we've been calling it a matrix-free approach because there's no matrix to compute, invert, multiply. All of these estimates just involve basically like dot products of your data, right? You compute the norm of your data, you have to compute this spillover terms of your data, but there's no matrices at all anywhere in this proof, so that's nice.
Okay, so thank you. So are there any other questions for Jay? Okay, so great. So vamos a tomar 10 minutos antes de segundo quiz. Bueno. Entonces hay una pausa, las personas que pidieron constancias, aquí están las constancias, entonces por favor vengan a recogerlas y recomenzamos en 10 minutos.